Welcome to AP Statistics. Today, we are exploring one of the most important concepts in probability, the binomial distribution. By the end of this lesson, you will be able to identify binomial random variables, calculate their mean and standard deviation, and use the binomial formula to find the probability of specific outcomes. We will break this down into three parts: defining the criteria, calculating the center and spread, and finally, calculating the likelihood of events. Let's get started. To determine if a random variable follows a binomial distribution, we use a handy acronym, BINS. Each letter represents a condition that must be met. First, B stands for binary. This means each trial has exactly two possible outcomes, which we usually label as success or failure. Next is I for independent. Each trial must be independent of the others, meaning the outcome of one trial doesn't change the chances of the next. N represents a fixed number of trials. We must know in advance how many times we are repeating the process, denoted by the letter N. Finally, S stands for the same probability of success. The probability of success, which we call P, must remain constant for every single trial. If all four of these conditions are met, then the random variable X, which counts the total number of successes, is a binomial random variable. Think about flipping a coin 10 times and counting the number of heads. It's binary, the flips are independent, there are exactly 10 trials, and the probability of heads is always 0.5. This is a perfect example of a binomial distribution. Once we confirm a variable is binomial, we often want to know what to expect on average and how much variation there is. The mean of a binomial distribution, often called the expected value, is the number of successes we would expect to see over many repetitions of the experiment. The formula is simple. The mean equals the number of trials, N, times the probability of success, P. The standard deviation measures how much the number of successes typically varies from the mean. This is calculated as the square root of N times P times the quantity 1 minus P. Let's look at an example. Suppose a basketball player makes 80% of their free throws. If they shoot 100 free throws, how many should we expect them to make? Using our formula, 100 times 0.80 gives us a mean of 80. We expect them to make 80 shots. Now for the standard deviation. 100 times 0.80 times 0.20 equals 16. The square root of 16 is 4. In context, this means that while we expect 80 makes, it is very common for the actual result to be about 4 shots higher or lower than that. We have now met our objective of calculating and interpreting the center and spread. Now, what if we want to find the probability of getting an exact number of successes? For this, we use the binomial probability formula. Probability of x equals small x is n choose x times p to the power of x times 1 minus p to the power of n minus x. This formula might look intimidating, but it is built logically. The first part, n choose x, counts the number of different ways or arrangements that we can get exactly x successes in n trials. The second part is the probability of success, P, raised to the number of successes we want. The last part is the probability of failure, which is 1 minus P, raised to the number of failures, which is n minus x. Let's go back to our basketball player. If they take only 5 shots, what is the probability they make exactly 3? Here, n is 5, P is 0.8, and x is 3. We calculate 5 choose 3, which is 10. Then we multiply by 0.8 cubed and 0.2 squared. This gives us 0.2048. So, there is about a 20.5% chance the player makes exactly 3 out of 5 shots. We have now mastered the calculation of specific binomial probabilities using the formal distribution function. To wrap up our look at the binomial distribution, it's important to remember that these probabilities represent long-run relative frequencies. In a real-world setting, or on the AP exam, you might not always use a formula. Sometimes, we estimate these probabilities using a simulation. To conduct a simulation, we first define a trial, then state the variable x as the count of successes. We repeat this many times, and finally calculate the number of successes divided by total trials. By using a random number generator or a deck of cards to simulate the success and failure outcomes many times, we can build a distribution of results. As we increase the number of trials in our simulation, the proportion of successes will get closer and closer to the theoretical probability we calculate with our formulas. Today, we covered the essential knowledge for topic 2.10. We verified the BNS criteria, calculated the mean, NP, and standard deviation, and applied the binomial formula for exact outcomes. You can now justify if a variable is binomial, calculate its parameters, and interpret those values in context. Practice is key to mastering these formulas. Make sure to practice identifying the n, p, and x values in word problems, as that is the most common hurdle. Good luck with your studies in AP Statistics.